record. Okay, so last class we started talking about stratified random sampling. So we defined the variance and the expected value estimates, which I think I have written down. Oh, I must have only, there we go. So we showed that the variance of, well, let's start with the mean. So the mean estimate based off stratified sampling is simply a sum of each individual estimate from the strata multiplied by this, what we can call the sampling fraction, which is capital NH over capital N. The variance estimate is very similar to what we had in SRS. The only difference here is that we now have this sampling fraction out front. So the W1 squared, that multiplies by the FPC for each population. And then we multiply that by sigma 1 squared over N1. So one of the questions that might come out here is, how do we treat the FPC in this question? The answer would be you would treat it on a strata by strata basis. So you could check the FPC in each strata, and you can apply it within the strata if it needs to be applied within the strata. That would be the idea. So it's the same concept as with SRS, the same rule as with SRS, except we would just do it in a strata by strata fashion. So if in strata 1, we don't need the FPC, we can move forward. If strata 2, we don't need it, we can move forward, etc. All right, and then we can show that the estimates for tau and for the variance can be found using the traditional adaptations of the mean. So we're just multiplying by the population size within each strata in this case to find the estimates given on slide 12. All right, we started working through an illustration to estimate the average, and we're also going to work through an illustration to estimate the proportion. Again, you can see here that the goal is simply we want to find 95% CIs for mu and for pi. So one thing we didn't talk about last class was the FPC part of it. We just worked through the calculation so that we could see how it would unfold in the stratified case. But we can go back and just talk about the FPC aspect of this now. So you can see in each case, we're going to have calculations that look like this. Here, maybe I'll just... Okay, so for strata 1, we'll have 1 minus 150 divided by 2,365. Okay, so this is 0.937. So we're going to keep the finite population correction in this case. In the second case, we have 100 over 1,297. Okay, so this is 0.923. And then in the third case, we'll have 1 over 250 divided by 9683. Okay, so this one we could have ignored. Okay. So we're going to keep the FPC for this group, and then we don't need the FPC for the third strata for houses. Okay, so then going back to our calculations here, in this group, we'll just knock this part out. All right, and then we should end up with the following.
So hello, Brian. So if FPC is bigger, if bigger than 0.95, so means we don't keep FPC.
Yep, that's cool. So then what we should get from this is 6.377065. Okay. All right. Okay, so we have use FPC, and then here we ignore FPC. Okay, and then this is because since 1 minus F is greater than 0.95. FH. All right, in part 2. Okay, so this, what's the rule for using the FPC? Right. So we use the finite population correction if 1 minus little n over capital N is less than 0.95. What we're showing here is for each strata. So for strata 1, 1 minus little n over capital N is less than 0.95. So we would keep it. For strata 2, 1 minus little n over capital N is 0.923, which is less than 0.95. So we would keep it. In strata 3, 1 minus little n over capital N is equal to 0.974, which is greater than 0.95. So we would remove it, or we would not use it, I should say. Okay, and that's the reason why. So this is the same reason that we established when we first introduced the finite population correction in lecture set 2. So the FPC only has to be utilized if the ratio 1 minus little n over capital N is less than 0.95. So here we remove the third one because it's not true, because that value is greater than 0.95. Does that make sense, Miriam? Okay, awesome. All right. In part 2, so in part B, we want to estimate the proportion. So this is going to be done in pretty much the same way as the mean. The only difference here is that we're talking about the percent contaminated. So these parts here, these are going to be the pi hat h for each strata. So basically what we're doing is we're just taking the average of these 3 proportions. So this process, the process of computing the estimate for the variation and the estimate for the total, or sorry, the estimate for the proportion and the estimate for the population average are going to be very similar. The only other consideration we have to make here is that when we compute the variance estimate, we have to use the SRS estimate for the variance of a proportion that we established in lecture set number 2. Now, one of the things here, and you'll see this momentarily when I actually write down the variance estimate, we haven't formally defined this yet because this is actually part of the, this is part of question number 7. No, yeah, question number 7, part A on assignment 2. Question 7, part A effectively asks you to write down what the form for the proportion estimate based off of a stratified random sampling and the variance of the proportion for stratified sampling would look like without numerical values. So what you're going to see here is a numerical example of the form of these estimators. And then on 7A, you basically just have to write down the formula for these estimators. So we haven't done that yet because that's part of the assignment question, but it's very easy to write it down because all stratified sampling is effectively just a weighted simple random sampling approach. So you weight the SRS estimators across each of the strata. Okay, so for example, for the proportion estimate, from above, you can see that we have the sum of WH times mu H. So we have WH times the proportion estimate plus WH times the proportion estimate plus WH times the mean estimate, sorry. So here we're going to have 0.177, that's WH or W1. And then we're going to multiply by the corresponding proportion for this group, which is 0.172. Okay, and then you can see the WH is the weight from the table on slide 13 in column 2. And the proportion estimate is the percent contaminated, but as a decimal, which comes from the second table on slide 14. So we're just weighting these 3 proportion estimates. And on question 7A on assignment 2, you're just being asked to write the formula for this approach. So you should be able to easily work out what the formula is going to look like just by comparing this calculation to the one given for the average. So we have 0.177 plus 0.172 plus 0.097 times 0.114 plus 0.726 multiplied by 0.132. And this is equal to 0.137. Okay, now if we want to compute the variance of, this would actually be a tilde. So if we want to estimate the variance of our proportion estimator, we're going to have basically the exact same thing that we had for the proportion estimator in the case of SRS, but we're weighting across each of the different strata. And then of course, as a result of this, because of how the proportion estimator works, or because of how the variance operator works, we have to square the term. So we're going to have something that looks like this. So we'll have 0.177 squared multiplied by 1 minus 150 over 2,365 multiplied by, and now what we're going to have is p hat 1 minus p hat divided by n minus 1, or n1 minus 1. Okay. And then, so here you're going to want to compare to SRS estimator for pi.
So 149 is 150 minus 1.
Yes. Okay, and then in the second case, we're going to have the exact same calculation, except we're changing the proportion now. So we'll have 0.097, 1 minus 0.097 divided by 99. And then in the last case, we can ignore that FPC again. So we'll have 0.726 squared, and then we'll have 0.132, 1 minus 0.132 divided by 249. Okay, and then just need to work this thing out real quick, like. Wait. I had the wrong proportion in there. Yeah, 114. Yeah, it barely makes a difference. Three zeros, yeah. All right, and then if we wanted to bound this, we would have 0.137 plus or minus 1.96 multiplied by the square root 0.000279. Okay, so this is 0.137 plus or minus. And then we have 0.104 to 0.17. Oh, it works out very close. Okay, so those are two examples of how to compute estimates based off of the stratified approach. So we have an example for computing the estimate of the average the estimate of an average using the stratified estimator. And then we have an example of computing the estimate for the proportion using the stratified estimator. On question 7A of assignment 2, that question is basically just asking you to write out these two formula in in terms of NH, WH, pi hat H, etc. So write them out as they would appear for the mean estimator, but in terms of the values that need to be entered in. So the condensed forms, or just the formula, if you will. And then in part B, you're actually asked to do a little proof based off of the variance estimate. Okay, the next thing that we're going to talk about in the stratified section is sample size calculation. And question 8 on assignment 2 is based off of the stratified approach and the effect that this has on the variance estimation. So to set this part up, we can consider a few questions that are related to stratified random sampling. So one question is, when is stratified sampling more efficient than SRS? And again, efficiency is something that we talk about in terms of the variance estimate. So we'll see calculations that we can actually utilize to determine which one is more efficient. So we can answer this mathematically. How should we allocate the total sample among the strata? And if an auxiliary variable exists, can we incorporate information from this variable to improve our estimate? And then the third question is something we'll talk about a little bit later, but this also follows from the simple random sampling approaches and whatnot. Okay, so in terms of allocation of the observations into each of the different strata, there's a few different approaches that we can utilize here. The easiest approach is what we would call proportional allocation. Okay. So in proportional allocation, effectively what we do is we let the size of each sample follow the same proportion as we let the proportion of observations in each sample be equivalent to the proportion of observations from the population that are allocated to each of the strata. So that's why it's called proportional allocation, right? So for example, if you have a population of size capital N, you split that population into H strata, and then each strata has capital N subscript H values in it. When we go to design the experiment, we will calculate some sample size, little n, and then we will allocate the observations into each strata, or we will allocate the samples into each strata, or collect little nh observations from each strata such that the proportion of values in the total sample size is the same as the proportion of values in the total population, right? So in doing this approach, what we have is the following. So we have the variance for mu strats under the proportional allocation approach is going to be equal to the sum from little h equals 1 to capital H of WH squared 1 minus little nh over capital NH multiplied by sigma squared h divided by little nh. All right, and then this is going to be equal to the sum from h equals 1 to capital H of WH multiplied by little nh divided by n. So this is an h, this is an n. Okay, so again, the reason that we're allowed to do this is because under proportional allocation, we are assuming that the ratio of capital NH to capital N is equivalent to the ratio little nh over little n. So you can see here, we're just splitting the WH squared term into two parts, and we're utilizing the fact that we have the same ratio within the sample when we open up this squared term. And then we have 1 minus little nh over capital NH multiplied by sigma squared h over little nh. All right, and then this gives us 1 over little n times 1 minus n over capital N multiplied by the sum h equals 1 to capital H of WH sigma H squared. Okay. All right. Okay, so let's recall question 1. Okay, so efficiency of SRS versus stratified sampling. Okay, so this is Q1 from slide 17, I believe. Okay, so the idea here, when will stratified sampling be more efficient than SRS or vice versa? When will SRS be more efficient than stratified sampling? So first off, the allocation method that we utilize for determining how the observations are going to be split among the strata, this plays into how we can comment on efficiency. So under the proportional allocation approach, we can write the variance of the stratified estimator as as follows, what is given here on the slide. Okay, so 1 over n multiplied by 1 minus little n over capital N, and then the sum across the strata WH times sigma squared H. So going back to this idea of efficiency, how can we comment on the efficiency of the stratified approach versus the SRS approach in the context of proportional allocation? All right, so for SRS, we have the variance of mu tilde is equal to 1 over n, 1 minus little n over capital N multiplied by sigma squared. Okay. And then just in case this is the same thing as 1 over sigma squared over n, just in case you don't quite remember it. Okay, so the stratified estimator under proportional allocation will be lower than the SRS estimator if the sum from H equals 1 to capital H of WH sigma H squared is less than sigma squared. Okay, so this idea of efficiency is effectively measured through a comparison of the variance of the estimator of the quantity of interest. So if we're estimating the mean, we can compare the efficiency of the approach by comparing the variances of the mean estimator from each approach. If we're estimating the total, we can compare the efficiency of the sampling approaches by comparing the variances for the total from each approach. Okay, that's the idea. So efficiency is basically measured through comparison of variation. So if we compare the stratified approach under stratified, sorry, if we compare the variance of the stratified estimator of the mean under proportional allocation to the variance of the SRS, or to the SRS, to the variance of the SRS estimator of the mean, it's easy to see that the only difference here is the sum across the strata compared to the sigma squared. So if the sum from h equals 1 to capital H of WH times sigma H squared is less than sigma squared, we would say that the stratified approach is more efficient, because then the variance of the estimator of the mean is going to be smaller for the stratified approach. Okay. So lower variance of mean lower variance of estimator of the mean leads to a more efficient sampling protocol. Okay, so that's the basic idea. Okay, so 1 minute. All right. Okay, so that's the first thing. And then we only have a minute left. So on Wednesday, what we'll do is we'll look at a sample size calculation within the proportional allocation scheme. And then we'll talk a little bit more again about efficiency, different ways of allocating the sample values to each of the strata. For assignment 2, so assignment 2, you can do up to question 7. For question 8, it says compare the differences of variances of mu strat under proportional and optimal allocation. Okay, so this is our variance for mu strat under proportional allocation. And the variance for mu strat under optimal allocation, we will have to derive on Wednesday, but I think, let me just check here really quickly so I can. No. Yeah, so we have the first part of this. So question 8, which is a comparison of the two variations, so the variance under proportional and the variance under optimal. I have to show you the variance under optimal stratification so that you can see what it is that you're supposed to compare. But that question is a pretty short proof where you're basically just taking the difference between the two estimates to get the form that's shown on the slide. So up to this point, you can complete everything on the assignment up until the very last question. And then once I give you the formula for the last question, which I'll give you on Wednesday, then it's just a little bit of a difference, a very short proof to work out the form in question 8. Okay, so stop there for today. Sorry, I took a lot of time to talk about the quiz at the beginning, but we'll do consistent lecture material on Wednesday. And if you have any questions, let me know. I have office hours after this. And yeah, just have a good couple of days, and I'll talk to you on Wednesday morning.